So first, I just wanted to say thank you all for being here. I had the pleasure of actually signing in most of you at the registration booth, so that was a bonus. I'm on the planning committee for this symposium, and again, I really appreciate everyone being here. As Anne just mentioned, I'm a PhD student here at Ohio State with the Byrd Polar and Climate Research Center and the School of Earth Sciences, and I work with fairy lions. So I'm going to talk a little bit about my dissertation work at Shackleton Glacier, and that's located in the background here. I wish I kept the original picture because it was Julie Mueller was skiing on the runway in the original picture I had. So I kind of wish I kept it. And this title isn't necessarily descriptive, so I added a secondary title. So this is The Search for Habitability in Antarctica. And I put this in quotations because, as you'll see throughout my talk, it has a couple of different meanings. So this is a little science heavy, but in a good way. So you've probably seen this image all over Byrd. This is the reference elevation model of Antarctica, REMA, produced in collaboration with Ian Howitt. And I'm going to focus on an area, the Transantarctic Mountains. So this is a large mountain chain that traverses the Antarctic continent and separates the east and western Arctic ice sheets. These mountains are tall. This is an image I took in a helicopter, hence why it's a little bit dirty, entering the dry valleys. And you can see these mountain peaks on either side of this outlet glacier here. So if you look at these soils in a little bit more detail, as Kathy mentioned, they're very arid. There's not a lot of water here. We're talking maybe 5-10 centimeters water equivalent per year in some places. They're very salty. If I can maybe use the mouse, this is a salt crust you can see on this rock. The temperatures are generally below freezing almost always during the year, and you have only sunlight during the Antarctic summer. Yet you still have organisms that can persist in these soil environments. So over here on your left, you have lichen. Next to that is the Columbella, the springtail, so those are micro-arthropods. You have your mites, and these are pretty much the biggest organisms that we saw at Shackleton with the visual eye, and these being very, very small, but still visible. And then you have your nematode worms and your tardigrades, so your cute little water bears. And really, these are the top of the food chain in Antarctica. And I want to emphasize this. There's not really diverse life that exists in these soils if you think about it compared to somewhere like here in Ohio. So these things that we probably can't see with the naked eye, most of them, that's the top of the food chain there. So what's interesting, though, about these organisms is if you look at their genetics or the phylogeny. So I put this quote from one of our collaborators, and it says that if you look at these endemic organisms in Antarctica, they represent a continuous chain of descent dating back to Gondwana. And what this means is that these organisms, despite being small and therefore not able to move when their environment starts to change by themselves, they found refugia. So they found suitable habitats in these mountain soil environments, and that they weren't necessarily just brought in by wind when the climate became more suitable. And this leads us to create some habitat suitability models. And this is a model borrowed from one of the co-PIs, Diana Wall, in Ross, Virginia. And this is looking specifically at nematode worms in the dry valleys, but I think this model can be applied to a lot of different systems. So if you're thinking about suitable habitats, they're defined generally by climate, salinity, organic matter, moisture, physical properties, and then we're learning that glacial history is increasingly more important, and I'll address that briefly in this talk. So a different combination of these factors can create either suitable or unsuitable habitats. So let's say you have an arid climate, high salt concentrations, and no liquid water. That's generally an unsuitable habitat. If you maybe have sort of the opposite of that, that'd be a really easily describable as a suitable habitat. And looking at these habitat suitability models, we can start to ask a couple of key questions. So how do these organisms persist and thrive in Antarctica if that unsuitable habitat that I just described was exactly Antarctica? And how do these biotic and abiotic factors influence their distribution? So these organisms are not ubiquitous throughout the environment. They're found in select soils. And I'm gonna throw this up here, thinking about habitat suitability in a different way. So how do underrepresented minorities also thrive and exist in Antarctica? And I'll address that more towards the end of the talk. So to answer these questions, we're gonna focus on an area, the Shackleton Glacier. Julie was a great introduction to the area. Again, she was the medic for the camp. But before I go into it in too much detail, I wanna throw up a refresher slide about the last glacial maximum. So the last glacial maximum was a period of time about 20,000, so we'll say like 18,000 years ago, where global ice sheets were at their greatest extent. And that's demonstrated in this, I don't have a pointer, in this first image, looking at modeled ice surface height or surface elevation height in Antarctica. So darker areas are areas that are higher, lighter areas are areas that are lower. So the snow accumulates at this dome and starts to be pressured into ice. Once it's pressured into the ice, it begins to plastically deform and flows downwards to the coast due to gravity. And that's demonstrated in the second image. So red is, or this image is looking at changes in height between modern and LGM modeled surface. So areas that are red were higher elevation during the last glacial maximum, and lighter colors are areas that were, not as high. And you can see that most of that red is along what was, pointed out in previous talks as this ice shelf area. So this is the Ross Ice Shelf. And if you look at the present modeled ice surface as this gray area and this dotted line, you can see that the model, so this dotted line, was much higher than present. So thinking about the Shackleton Glacier, it's a major outlet glacier of the Eastern Arctic ice sheet. It's located approximately here. It's an area that has undergone significant elevation changes in ice throughout time from the last glacial maximum to today. So why do we want to focus on the Shackleton Glacier? Well, first, the image that you see on the left is the Shackleton Glacier. The ice is here, sorted down the middle, and you can see these ice-free areas on either side. So we have several of those ice-free areas, which is a benefit of this region. And I'd like to point out Bennett Platform here, because Bennett Platform, and like many of these sites at Shackleton, have locations with different glacial histories. So this blue line in this image is the modern ice surface, so that's what it is today. And this dotted line is what it's modeled to be or predicted looking at the LGM surface from a different glacier. So this is an estimate and extrapolation. So if I'm looking at, let's say, a point in the middle of this triangle, this soil right there is now currently exposed, but it was potentially overlain by the glacier during the LGM, different glacial histories. We have different reproducibility across elevational and latitudinal transects. So these sites down here are lower elevation, similar elevation. As you move towards the polar plateau, so further south, you end up with sites at higher elevation. But then we also have the benefit of having, again, this latitudinal transect. Looking at Bennett Platform and Mount Augustana, those are at similar latitudes. So those sites have likely undergone similar climatic conditions. As I mentioned in a previous slide, we have simplistic ecosystem dynamics, and it's among one of the least human-modified terrestrial ecosystems on Earth. In fact, it was really cool. Some of these sites, we were probably the only people who have ever been there. So at Shackleton, we visited 12 locations along the glacier, and we collected samples at 3 transects at each site, trying to get samples that were maybe exposed during the LGM, so these older soils and soils that were covered by the glacier 20,000 years ago. In total, we collected about 230 samples. All of those were leached with the help of an undergraduate here and analyzed for major ions, nutrients, perchlorate, and then a suite of other specialized measurements that can help us understand maybe the sources of the salt and glacial history. But in the interest of time, I'll focus mainly on the water-soluble ions. And in the upper right, that's a picture of me at Taylor Nunatak, sampling soil and digging a soil pit. So somebody mentioned earlier about having shovels to still dig. Yeah, we still have shovels. And we're collecting a soil pit there at Schroeder Hill. To give a little bit of perspective about this camp, this is actually the first image that I took walking off of the airplane. And full disclosure, any image that you see of myself was not taken by me. I'm a good millennial in the sense that I take lots of pictures, but a terrible one in that they're not of me. So thankfully, the lead PI, Byron Adams, took those images. So here at Shackleton, you can see the tents that we stayed in over on the left. Our recreation, or I'll just say our galley tent, is that long rack tent in the middle. And then I don't think you can see Julie's tent. It's right past this person, but it's there, I promise. And this is our like fun tent. So we visited all of those locations by helicopter. We had amazing helicopter pilots, and they were so involved in our research. Those Columbella and those mics that I pointed out, they would stop at every site that we looked at and start picking up rocks to try and find them. And in fact, some of the Columbella, most of them we found were our helicopter pilots. They got very excited. So in the center is Ian Hogg, our Kiwi Canadian colleague, Noah Fuhrer, there's myself, and Diana Wall over on the far right. So we went to each of these sites, and like I said, we collected soil samples. This is me, bright pink gloves, purple scarf, blue glasses and all. And when you look at these soils, they tell an interesting story. So I'll show this image at least another couple of times. And what we're looking at is still the Shackleton Glacier. The orientation is flipped, so now north is pointing to the left, and the ice is here and the ice-free areas on either side. This image is looking at frequency of biomass, detectable by nucleic acids. So what they did is they took all these soils and they tried to sequence all these nucleic acids and try to find any signs of life, just broadly. And some locations in the blue that have biomass are fully, all these soil samples had biomass, but then you have some locations where not a single sample collected had any sign of life. And again, this is using nucleic acids. So this is an entirely sterile environment. And I'd like to again point out that this is the only surface environment that I know of as of now that has absolutely nothing that we can find in these soils. And it also is an attest to our great sampling that nobody sneezed in the bag or stuck their finger in. That we were able to really collect these great samples. But then what about these locations in the middle? Why do some of these sites have blue areas with biomass, and why do some of them have no biomass? And this is really the story that I'm trying to piece together using chemistry. There's the magic word, chemistry. So here I'm looking at a simple metric. So this is looking at nitrogen to phosphorus molar ratios. And these concentrations are very variable. We're ranging over 7 orders of magnitude on this y-axis. To put it in perspective, if I were to collect soils even around the United States, I'd probably only be somewhere between 1 and 100, not 0.1 and a million. And then here we're plotting all the samples with distance from the coast, so starting off at the Ross Ice Shelf and moving further inland. There's a general scatter of these points, but I'm drawing this line here of N to P equals 16. So if you remember from your oceanography courses, this is the Redfield ratio of 106 carbon to 16 nitrogen to 1 phosphorus. And while we're not talking about the ocean here, because this is the ideal ratio for phytoplankton, I'm using this as just a general metric to start to understand maybe some samples that might have nutrient concentrations that might be suitable for life. So looking at this distribution, we want soils that are either at that line or in this environment, preferably below it. And that's generally in this area that's closest to the coast. So that's that Mount Speed, Nielsen Peak, Wasco area. And what was unsurprising about this graph is these were actually the areas that we found the most diverse life. So within this red circle, you can see these little white lines, and those are actually the Columbella that we found. And then this rock down here, this is a granitoid with some lichen on it. And again, these are the only, whoa, how did that happen? Jason? Okay. Sorry. So these were really the only sites that we could visually find life just in the field with the naked eye. But I want to circle back to what I said earlier about these high nitrate concentrations. So why are some of these samples so high, and how can we use this data to really understand a different parameter of our soils? For that, I'm going to talk about something called wetting ages, coin termed by Byrd. So looking at the nitrogen cycle, and I borrowed this image from NCAR, so it's simplified. You have nitrogen that enters soil environments through some sort of fixation. You can have mineralization, nitrification, denitrification, and then maybe some gaseous loss. You also have precipitation, bringing down nitrogen to the soils. But like I said, Antarctica, the ecosystem dynamics are simple. So you can actually get rid of pretty much most of this graph and focus on wet and dry deposition. We can look at the concentration of nitrate on the soil surface, and using the deposition rate that we can calculate from ice cores, we can start to estimate how long these soils have been exposed to the surface without water. Nitrogen salts are extremely soluble. Anytime that there's any precipitation, it's going to wash away these salts and restart that clock. So looking at what the deposition rate is, we can start to calculate what these wetting ages are. Using those calculations, we can start to plot this spatially. And this is looking at Bennett Platform here on the left. And you can see the wetting ages span, somewhere around the order of really, really young to 800,000 years. Bennett Platform was a unique site for us. It was the only site that we could visibly see the glacial history of the area. As the glacier advances, it pushes sediment with it and creates terminal moraines. And those are these bathtub rings that you see along the valley. And it's even more apparent when you're on the ground. So the glacier came approximately this far into the valley, pushed sediment with it, and started to rebound back and forth as it retreated to its current position. So if I draw that line of the approximate glacial history, or the LGM trim lines, that maximum extent, it's approximately here. And we can see generally that the samples that are below that line have lower wetting ages, so they've had liquid water more recently, than soils that are above that line that have been exposed for much longer. But this information is helpful for those discrete points, but we want to understand the region a little bit more in detail. And to do that, we can look at something called an interpolation, specifically an inverse distance weighted interpolation. So I know that's a lot of words, but what it means is if let's say I'm trying to look at the soil chemistry at this one point, I use the points near it to estimate this chemistry and weight them differently depending on how close they are. So because this arbitrary point that I selected is closest to this one and further away, this soil will have more of an influence on its chemistry than something further. So if we run the IDW interpolation, we end up with an image that looks like this. Remembering that that trim line came approximately this far into the valley, this greenish yellow, maybe on your screen, is about 10 to 25,000 years, which is where we think, or what we know from the glacial history of the area, that the LGM was about 18,000 years ago. So if we're thinking about soils that we might look at to find diverse life, it would be maybe here. This would be a good place to look because it's had liquid water more recently. And we can do something similar at Thanksgiving Valley. So this is a site that we know less about. So same wetting age calculation, and we can run the same interpolation. So now this being the Shackleton Glacier on the left. So we think that the Shackleton Glacier probably intruded about this far into the valley. This would be maybe a place to look for life, had liquid water more recently, thinking about that habitat suitability model. And then as you move further inland, you start to have these really red areas. So like big no, there's probably nothing living there. And what's interesting about this site, because again, we don't know as much about it, is that the other side of the valley has lower wetting ages again. So maybe during a previous glacial period, this glacial tongue intruded or overlaid these soils, or maybe there was some inundation. We're not entirely sure. What we do know is that we can start to pick out soils to look at. So like maybe here and some of these hot spots up there. So putting this all together, looking back at this broader image of Shackleton, we can start to make some general, or start to point out some general trends. So as you move from the coast further inland, you're decreasing in your biomass, but you're also increasing in elevation, you're increasing your nitrogen to phosphorus ratio, and you're increasing your wetting age. So thinking about these better habitat suitability models, we can start to look at these more specific parameters. To find a suitable habitat, we should maybe look at soils that are lower in elevation, have a lower N/P ratio, and have been wetted more recently. So the toxicity of an environment really can dictate whether organisms can persist, but you can have influence from other variables such as winds that Kathy mentioned previously, or glacial history, so advanced retreat of these glaciers, that can create suitable habitats. So circling back to what I mentioned earlier in my talk about suitable habitats, I want to start to talk about the variables that can affect habitability for other organisms, like me. So this is an image that Byron took of me in the field. Fluffy pink gloves, kind of ridiculous scarf, but my mom made it, and it's the warmest thing in the world, and a hat that's far too big. And I'm smiling in this picture because my experience at Shackleton was phenomenal. And in fact, my previous experience in the dry valleys was awesome too. So this picture is up on the slideshow, and we had a lot of fun with our team. So this was Byron and all the team entering the C-130, and I was promised that we would go on a Basler or a Twin Otter. So when Byron's like, Melissa, we're going on the plane to Shackleton, turn around, I was very disappointed to go into the C-130 because it is not the best thing in the world. But the helicopters were better. This is Ian Hogg, and he's probably one of the funniest people I've ever met. And we did work really hard, and our mountaineer, Jeff, was great in helping me dig some of these soil pits, because some sites we touched down and the helicopter pilot says, okay, I'll be back in an hour. And we had a lot of ground to cover. And we did have some time, though, to really take a minute and look at how beautiful the Shackleton Glacier region is. And this is an image of me looking out on the glacier towards Mount Hegan from Bennett Platform. And it's truly the most beautiful site I've ever visited. And what's great about this team is that it wasn't just the experience at Shackleton that was transformational, but we had a great time afterwards as well. Here's an image of us at University of Colorado Boulder. We had a PI meeting. So after this great weekend of sharing our initial results, Byron, the lead PI, and Nate, Diana Wall's former postdoc, we climbed up the Flatirons and had a great end to this PI meeting. So thinking about how these underrepresented minorities survive and thrive and persist in Antarctica, the answer to that question, in my opinion, is pretty simple. You need supportive teams. So this is the last image of us leaving Shackleton Glacier, and we are leaving on a Basler, which is pretty great. I was very happy. And we had such great support from everyone, and I include Barry here because he's probably my biggest fan and who's really been a supporter throughout my entire journey through science. You need role models and pioneers, and that's Marcy Shaver-Adams and Diana Wall, to be there and to pave the way and serve as role models so that people can persist in these other environments. So I think I'm out of time. I saw Anne holding the thing. I'll leave my acknowledgements up because this work can't ever happen alone, and we've discussed that in great detail today. Thank you.